Today we're going to look at the fluff challenge on ROP Emporium. So the description says the concept here is identical to the write for challenge. The only difference is we may struggle to find gadgets that will get the job done. However, if we take our time to consider all the options, we'll succeed. And again, we're going to start with a 32-bit binary before we move on to the 64-bit. We have some more information on the page, a little bit shorter than usual, and essentially here we're being told to work backwards, try and find something, a gadget first to write to memory, and then work our way backwards, which is a hint that there isn't going to be an easy way for us just to move. But we'll have a look at that in a second. We can see that there's a questionable gadgets. We normally have a useful gadgets segment which has some gadgets to help us out. This time it's questionable gadgets, but the general challenge is the same. We need to call the print file function with the path to the flag as the only argument, so we need to write the path of the flag to probably the .data section, which is the 8 bytes we've been using to write flag.txt in the past few challenges. So let's move on to the challenge. I'm gonna try and cut down the amount of time going through some of the usual checks and like typing out things slowly, because if you've been following the videos up until now, you should have a good handle on that, or if you've been working through the challenges yourself, again, you should have a good idea. But we will still be finding the EIP offset and stuff, even though it's likely to be the same. But we'll just try and speed through some of the. So we'll open this straight up in pwntools and start off by finding the offset to the instruction pointer. So we'll generate a cyclic pattern of 100 and copy that, run the application, paste it in. We've crashed it, we've got a stack and we've got our registers here, so we'll search using cyclic-L to find the offset of the EIP, which was 44 as usual. And now that we have that out of the way, I'm actually going to open it up again just to get rid of some of the functions that would show up whenever we try to disassemble here, just see if there's anything new. But it looks like we just have our main, we have our pwn.me, and then the print file, which we're looking to call. We have this questionable gadgets instead of the useful gadgets, but let's disassemble the useful function first. Oh yeah, that's just the print, where we call the print file from. So let's disassemble questionable gadgets, and you can see we have some gadgets in here. The challenge advised us to work our way backwards and first try and find our move instruction. So normally what we have to write towards the end of the challenge, our goal is to write 4 bytes from, say, flag or .txt from a register into a memory location pointed to by another register. So let's see if we can find a gadget to do that. Okay, so if we search ROPER-F a file and pass in fluff32, and then we can do -- search and search for move. And what we'd be looking for here is the move and then dword pointer with a register inside the square brackets, and then another register, so that we could send the flag and the .txt string from one register that we control into and write it to the memory address of another, to the memory address using another register that we control, which we don't have in this example. So this is what the challenge was hinting at, and why we would need to look at the questionable gadgets section. So although we don't have a write option, we have an exchange. We have an exchange instruction here. Exchange whatever's in the DL, which is the least significant 8 bits, the least significant byte of the EDX register, into a memory location pointed to by the ECX register. So this exchange is essentially like the write, except it'll exchange whatever's in here with whatever's in here, and vice versa. So if we can control the DL, the EDX, and we can control the ECX. Then we can write to say the .data section, which we've been writing to previously. So we essentially need to trace things back from here. So we have this instruction. We need to, let's make this a little bit smaller and open up Sublime, and let's just try and lay out the structure here. So if we want to write, we need to do this exchange. So we'll exchange let's say, we'll say, yeah, we want to know it's a byte. Let's say, we'll just put the whole thing here, byte pointer, ECX, and then we have our DL, which is EDX. Okay, so we can grab that address, and we need to control then the ECX. We need to put our data section memory location there, the address there, and we need to control the EDX to write some of the characters from our flag.txt string. So can we pop to ECX? Well, we have a pop to ECX here, but it's followed by bswap ECX before it returns. So if we try and have a look here and see what pops we do have, we have quite a long chain here with the pop ECX. So our shortest chain with the pop ECX is the pop ECX and then bswap ECX. So if we were to have a look here, bswap reverses the byte order of a 32-bit or 64-bit register, so it'll convert from little endian to big endian, or vice versa. So if we want the data to be in little endian format, we know this is going to reverse it to big endian. So if we just put it into big endian first, then we don't need to worry about this bswap. That'll just undo our operation on it. So that's fine. So we'll have let's grab this address. And that is our bswap. And then we also need to control the least significant byte of the EDX register. So we can have a look here. Do we see any pop EDX? Don't see any pop EDX there. Let's search. Okay. That might only search by operation rather than by... Yeah, okay, it searches by operation. So there is no operation for us there. Let's have a look at our questionable gadgets. And we have this other operation here, so px, edx, ebx, eax. So let's have a look at the px instruction. Parallel bit extract. And the px uses a mask in the second source operand, so the third operand, to transfer either contiguous or non-contiguous bits in the first source operand, which is the second operand, to the contiguous lower order bits in the destination, which is the first operand. For each bit set in the mask, px extracts the corresponding bits from the first source operand and writes them into contiguous lower bits in the destination operand. The remaining upper bits of the destination are zeroed. So let's have a look at what we have here. We have px, edx, ebx, eax. So the mask is the second source operand, but it's the third operand. So the mask is the eax. The source operand is the ebx, and the destination is the EDX. We need to control the EDX, so this is how we need to write to it. And if we look here at the full instruction block before the return occurs, we have a move EBP to EAX, and then we have this arbitrary value baba baba, which is moved to the EBX, and we have here the EBX and the EAX. So if we can pop some data into the EBP, we know that that will be moved into the EAX. So we control this value, which here is the third operand, so it's the mask. So this example shows the masking operation, and then we have our PX. So it's going to perform the mask using this arbitrary value that they've set. The value, it's going to perform the masking against this value using the mask that we supply through the EAX register, if we can control this EBP. At the end it has this instruction move, it just moves dead beef to EAX, but at that point it returns, and we would need to be doing this for each character, because we can only write 1 byte at a time, this lower order byte, using the exchange function anyway. So we would need to do this in a loop, so it doesn't really matter that this does the move 0x dead beef at the end. So let's get that out of the way. We have our instruction here, and we'll call that a long px gadget. So this is going to get our if we use the correct masking value against this value, we'll be able to put our characters into the EDX, and then using this value, we'll be able to pop our data memory address location into the ECX, and then we'll be able to do the write here by exchanging this byte that's in here. So let's try and put it together so it hopefully make a little bit more sense. So we need to pop to the EBP here. So I can't see pop EBP here. Let's go back and have a look. Pop, and here we have a pop EBP. Okay, let's put that in there. So we're going to be going through the loop and saying in flag, for each char in flag.txt, do this, where each time we're popping the data section address in here, data address offset plus the index plus loop index. We'll just call that index. And in here for popping EBP is where we would be popping this char in, ready for this. But obviously we're not just going to be popping in flag, because what will be happening there, if we pop in F, it's going to do a masking operation using F against baba baba, and that's not going to result in F. So we need to find out what character, what value can we perform that operation with against, can we perform the operation with against baba baba in order to get F. Hopefully that makes sense. We'll try and go through and have a look at some of the code here in terms of how to put this together, and maybe explain it a little bit further. So let's open up the pwntools script, and this is the usual script that we look at. We'll just have a look at the structure here at the same time. So this is the usual template script. We have the binary being loaded and the context being set, so we don't need to worry about that sort of stuff. We're finding our instruction pointer automatically at the beginning. but we know it's going to be 44 anyway. And just as usual, we have our data section address, which is the offset of the .data section, where we know we have 8 bytes free. I'll not go into checking all that stuff. We've done that in all the previous videos. And we have our print file function as well, which we know we need to call at the end. So I've basically just plugged in the values here. Our pop EBP, you can see the BB here. Our long gadget is right here, ending in 4.3, and then our bswap gadget is ending 5.8, and then exchange is ending 5.5. So again, we have to explain this in reverse order as we would be building it. We have our exchange operation, which is going to write 1 byte from the EDX, the lower part of the EDX, which is the DL. It's going to exchange a byte from there into the memory location pointed to by the ECX. So we need to put in this .data section address into the ECX, and we need to put in a character that we want to write into the DL. So in order to do that, we have this exchange operation where we can, in order to do that, we have this bswap operation where we can swap the, well, we pop a value to the ECX. This is going to be our .data section address, and because it swaps the endianness here, we just need to reverse the endianness before we pop it. We to get our EDX value in there, the character we want to write, we have our long gadget here, which is going to move the value we give it to the EBP, and then it's going to move this baba strings to EBX, and then it's going to perform this masking operation using the value that we've popped into the EBP against this baba, and then the result is going to put in the EDX, and then it's just going to do something here that we don't care about. And that EDX is going to be used down here with the write operation. So to just explain what we did before, what we mentioned before in terms of the characters in the flag, we're, instead of going through all the characters in the flag, we're going to be going through the values that we need to mask against this baba in order to write FLAG, 1 by 1. And it's 1 by 1 because we're doing the byte pointer here. We're only working a byte at a time. So we already have the mask in here. I'm going to go through that in a second. But in terms of the code here, we have our mask, and then we're looping through each character in the mask, and we just have an index here as well, which is going to be our data section offset, and we're popping the mask to the EBP. We perform this masking operation with that character of the mask, that value. We we pop our data section address to the ECX, and we just make sure it's in big endian format, so because it's going to be swapped here as well. And then finally we do our exchange. So we exchange the value that we've now got in the EDX, the lower part of the EDX, with the whatever's in the memory location pointed to the by the ECX, which we've just put this into. And putting that payload together, we just flatten it with the EIP offset. We're putting all this fluff exploit, we put all that in there, and it'll flatten it all for us. And then we're just calling print file with our data section address as a parameter. And just before I go through testing that out, I'll go through how we were able to get this fluff mask. You can see here I've just mentioned that it was calculated in a separate script called findmask.py. So let's have a look at that. So I'll close the Sublime out of the way, and let's go ahead and open up this mask, findmask.py. Okay, so I had looked through some resources online just in terms of how this masking operation would occur. You can actually see some pseudocode in terms of how to do this, and there are some other examples to compare it graphically. But let's I can't close the calendar. Okay, there we go. What did I do here then? So we've got a target string that we want to get, which is flag.txt. We know that what we're going to be comparing it to is baba, and we just want to store our mask as so we can print it out at the end, so we can just plug it into our program. And what we're running here. So we're running through each character in the target string. We want to calculate what's the mask for each character. And first we just print out, we're printing out in bits and in hex the hard-coded value, and just for the visual, it was mainly just for debugging as I was going through it to make so I could manually verify that it was, and I'll try and show that whenever we run it. In terms of actually calculating a mask, so this is the mask for each character. So for one character we need a hard-coded count and a char count here. I've reversed the order of the bits just because it's easier to go through, because I'm working from the small end of the binary to the bigger end. It was just easier to, in terms of dealing with the Python loops, to reverse it. It was easier for me anyway, logically. So I reverse the orders of these, and in doing that, changed it to little endian. This is just converting it to unsigned int a 8, unsigned int 8, and then an 8-byte unsigned int, should I say? And then we're getting the bits from it here. And then we'll loop through each bit in our character. So say the first character is F, going to loop through each bit, and we'll perform our masking operation here. So what we essentially say is, if the bit in the hard-coded value bobber matches the bit that's in whatever character we're trying to do at the moment, say F, then we add a 1 and increment our char count. If not, we add a 0, and we always increment our hard-coded count, but we only increment our char count if we found a bit to represent the bits that's in the char. I know that didn't sound very good. I'll try and give a better visualization, visual of that in a second. In terms of what's happening with that loop. So just to move on, just try and jump through some of this. We then just pad this out with zeros, just because we're later on going to be converting to unsigned int 16 bytes. Yeah, 16 bits. I might have said 16 bytes earlier. Yeah, but anyway. So yeah, we pad that out. We reverse this because I reversed stuff earlier on for doing the loops. We reverse that back to how it should be. We've got our results. Let's append that to the full mask, which we're going to print out at the end, so we can just copy and paste it. And then here this was just some debugging that just print out as it was going. So let me try and run it and just explain a little bit. Hopefully I'll be able to explain a little bit better what's going on. Let's run find mask. You see it's run through. So for each character, we have here the characters flag.txt. For each character, we have our key, and we have the way to work this out. Basically, I've put it in this format now in terms of printing it. But the way to work this out is we have our key, and we have our char that we want, which is F. So we need to see which ones of these match. So here we've got a 0, 0. So in that case, they both match, so we write a 1 to the mask. Here we've got a 1, 1, they both match, so we write a 1. Here we've got a 0, 0, they both match. Oh, sorry, here we've got a 0, 1, they don't match, so we write a 0. Here we've got a 1, 0. Oh, sorry, but then this carries over. It's probably a little bit better to explain go through visualizing this in the diagrams, because it's I'm not going to be able to explain it as well. But essentially we go through that. We've calculated our mask for each one. We print out the mask in hex and in binary, and then at the end we just print out the full mask in binary and in hex. So these hex values are the values which I copy and paste into the program, and this is the mask. So In terms of whenever I was calculating this initially, it took me a while to do in terms of messing around with this bits and unbits and getting the sizes of things right and the order of things right. Maybe the way I did this in terms of reversing things, and there's probably a far easier way to do it. I would say that this, I would go as far as saying that this kind of functionality, there's probably just a function built in somewhere that I don't know how to use, probably in pwntools. So if anybody has a cool, quick way of doing all this, I'd be interested to see it if you mention in the comments. But anyway, all that plugged together leaves us with that script, which we can now then run pwntools debug, and you can see here that we've got a flag printed out. So it found our offset automatically at 44 bytes. We've printed out our addresses here, which we put in manually anyway. It's just so we can have a look at that and see what's going on. And then we've got a flag. So let's have a look at a more efficient pwntools script, or a script that at least is a little bit shorter and makes use of the ROP object and functions to simplify things a little bit. Okay, so let's close that down and open up the AutoPwn script. And in this one, we could have just copied and pasted the thing that automatically found the offset, but I just put it in here manually to shorten out the general code size. And let's take this out, the print in the ROP gadgets. We create our ROP object here, and we find our data section through the elf symbols rather than manually. We find the long px gadget just by using the questionable gadgets offset, and the same here with bswap and the exchange, because for some reason they just don't show up in the ROP.find gadget, which I just, again, I mention this every video, but it just seems crazy to me. It feels like there must be a way to just search for those without doing it manually. I thought that was the point of pwntools, but maybe I'm wrong. Probably not. I probably just don't know how to do it. But we assign all our gadgets anyway to variables. We have our full mask, which we've pasted in, but we could just introduce that script into this one, or we could call that script from this one. But I mean, it's just as easy, or probably easier, just to copy and paste it here now that we've got it. This is the space saver. So, well, not really a space saver, but it's cool. So instead of looping through generating our payload kind of manually, we've done ROP.raw, and we just passed in each of the parameters for each character. So this entire loop is just each character is done in one line of this ROP.raw. But the logic is exactly the same as the previous example, so I'll not go through everything there. And then we just call print file with the data section address, so we don't even need to worry about the location of that or lining up our parameters or anything like that. And then we generate a ROP chain, print it out just to have a look at it, and then at the offset, which is 44, we inject this ROP chain that we've built. So with that done, let's try and run Python AutoPwn, and you can see here that we have got the flag as well. It printed out all the locations, memory locations, and we have our hex dump of the ROP chain. Now that we've saved the payload, we can always use this payload later, so we can just now run fluff and pass in the payload. And we get the flag. Alright, so let's move on to the 64-bit binary. So let's open this in pwndebug, and we'll just get the cyclic pattern out of the way, just in case they've switched up the offset on us, or in case our offset finding function in pwntools script doesn't work. We can't see the cyclic pattern in the RIP because it's not going to try to load an invalid address, so we grab the first 4 bytes, the RSP, do cyclic-L, and just confirm that we've still got 40 bytes that we need to write before we can actually start our exploit. Now that we've got that out of the way, let's have a look at the questionable gadgets function. So, as in the previous example, we didn't have a move operation where we would just be able to write our flag.txt to a memory location of our choice. This time what we have here is the stos operation. We can see here it is taking a value from the AL, which is the least significant byte of the RAX, and putting it into a memory location pointed to by the RDI. So we know that we want to be able to control this RAX. We can get our characters in there, our flag.txt, and we want to be able to control the RDI to get our memory address in there. But let's see what this actual operation does. So I hadn't heard of stos before this. If we search that and go to the first link, we see it stores a string, and in 64-bit mode it stores a byte, word, a double word from the AL register into the destination operand. The destination operand is a memory location, the address of which is read from, and then we can see there the registers. So in terms of controlling those registers, let's make sure that we can, if we do ROPE-F fluff and search for pop, we can get this pop RDI address, and that'll get us our memory address offset into the RDI for that operation. But we also need to control the RAX to get into this AL. So it doesn't look like we have a pop RAX here. So as usual, as in the previous example, we'll go back and have a look at the questionable gadgets and see what else they might have left for us. In terms of RAX, we have this no op at the bottom. Don't worry about that. We have this bx function. So this is all one chain where it's going to pop RDX, pop RCX. It's going to add this arbitrary value to the RCX, and then it's going to perform this bxtr operation with those registers. Nothing there with the RAX, and there's nothing. Doesn't appear to be anything with the RAX here, but it's our last thing to check. So let's see what this xlat instruction does. So we can see that it's using it's accessing a memory address pointed to by the RBX. So let's go and have a look at the xlat instruction. Table lookup translation. So it locates a byte entry in a table memory using the contents of the AL register as a table index, and then it copies the contents of the table entry back to the AL register. So the AL register is what we need to control here, the stos. The AL is the least significant byte of the RAX. So this is going to take the memory address location from the RBX variable, memory address pointer, and place it in the AL, the bottom least significant byte of the RAX. So as it's operating in bytes, again, we know we're going to need to loop through doing each character at a time, and we now know that we can control the RDI, we can control the RAX using this instruction, but we need to be able to control the RBX here. And this is where we can see that we've been left another gadget. So let's look this up. bxtr x64. Okay, bit field extract. This extracts contiguous bits from the first source operand, which is the second operand, using an index value and length specified in the second source operand, which is the third operand. Bit 7 to 0, the least significant bits of the second source operand, specifies the starting bit position and the bit of the bit extraction, and the remaining bits specify the maximum number of bits beginning at the start position to extract. So let's see what our gadget was here. The first source operand, which is the second source operand, RCX, is going to... Okay, so the third value is the RDX is going to be where the length and the index value and the length is specified. The RCX is going to be where the bit extraction is applied to, and then the result is going to be stored in the RBX. So we need to be able to control the RBX in that scenario, and we can see that we're able to control RDX and RCX to get our values in here. We can see there's this arbitrary add operation, and then we need to, and then that's going to be written into the RBX. So let's have a look into that. So we'll open up the pwntools script here and just try and go through each section to hopefully be able to explain this a little bit better. So I listed some URLs to some write-ups and some scripts from other people who solved this challenge who can probably explain it maybe better than me, particularly this blog. It helped me in understanding the logic behind it anyway, because most of these operations are things that I've not seen before, and obviously I'm doing these challenges because I'm trying to learn how to solve them. So yeah, we just plug in our addresses as usual, our data section address. I'm not going to go through that. We got get that same way as we have done. We find our EIP offset automatically. We've plugged in the address to those gadgets that we were just talking about, and let's just try and go straight down to the actual code. So we're writing we have a variable here with the flag.txt, the string we want to write to memory, and in the previous examples we were able to control the register. We were able to put, say, F or into a register and then write it to the memory locations which we had at like the .data section or something like that. And then in other examples we did something similar, but we had to like XOR it, or we had to do the masking operation and stuff like that. In this example, we're actually finding each one of these letters inside the executable. So you can see here we loop through each character that we want to find, and we read the fluff executable, and then we're calling find, and we're looking to find this character somewhere inside it, and then we're just also adding on the elf address, so that just where the executable starts. In this case, we could have hard coded it, but I've just put that in case that would change, and then we're getting the hex value of that. So let's just find us the memory address, saying where in memory can we find F, where in memory can we find L, etc. And then it's just going to print those out and add them to an array. And then here we're going to go through and loop through each of these memory addresses for each of those characters which we want to write. You can see here we've defined a current RAX which we've set to B, 0xB. So I'll show you first how we found that before explaining why we've set it. So if we go back to let's close that down, go back to our GDB, and let's try and set a breakpoint at pwn plus 150, hit run, and then enter. And essentially after this runs, we can see that the RAX is initially set to B, so whatever value that's set to. And the reason this is important for us is whenever we're going through this loop, we are modifying the RAX, but each time we go back to the loop, the RAX is equal to the value it was at before. So it means that each time we do that, we need to subtract the value of the character that came before it, the memory location, because otherwise we keep on adding the offset to the point where we're not actually getting close to the character in memory. So in terms of this loop, we we're looping through. The first time that we loop through, we're just using this current AEX. So if it's not equal to 0, we're going to change the current RAX to string to write, so to whichever value in here is next in the loop. And then we are performing our bxtr operation. So first of all, we pop our RDX, which is our index and length. So you can see here length is 40, which is 64 bits, and then our index we just have a 00, and the RCX as well, which is the current character location. So we're popping the character location on here, which we've defined, which we've found here, and we subtract the current RAX from it. So because the RAX, it wasn't set to 0 initially, we subtract that. The next time we go around, we'll need to subtract the memory address for F, etc. each time we go around. And we also need to subtract this hard-coded value because the next instruction in this ROP gadget was to add this value to RCX. So if we subtract that, then it'll counteract that operation. And then finally, we have the bit field extract. So that's going to occur where it's going to use the length and the index we've set here in RDX. It's going to use the current RAX value and memory location. Sorry, it's going to use the the current RAX, which is the memory location of the current character, and it's going to place the result in RBX. And then we need to get the RBX into the RAX ready to actually write it. So we perform this bxtr. We're moving the bxtr results. We're using the xlap-b operation here, and that's taking our result from here, the RBX result, and it's placing it into the RAX, the AL part of it. It's just 1 byte, ready for our final operation. And our final operation then is going to be this stosb, where we store the string byte from our AL, where we've just moved the bxtr result to into the memory location pointed to by RDI. So we need to pop RDI, and we're going to pop the data section address with the I offset to the RDI, and then this will be called using our current character and the data section address. I hope I explained that okay. It's going to loop through that each time, and then finally we just plug this exploit that we've compiled into our payload. After our 44 byte offset, it's going to be 40 here, and before we pop our data section address and call print file. Okay, I hope that made some sense. Let's try and run it. Okay, you can see it's found our offset here at the start. We've just printed out our addresses for our gadgets and our functions and data section and stuff. And then you can see that we had the loop here where it initially finds the addresses, where it's print out to say, okay, we found F at this location, we found L at this location, and it found them all. It compiled the exploit, and then it gave us the flag. Hopefully that made sense. Let's have a look and see the autopwn script to see how we could improve that or simplify some of the code. So if we open up the autopwn script, as usual, we just manually put in our offset here. We create a ROP object using the executable, and finding our offsets, where possible, we just use like our elf symbols. You can see here we've done that with questionable gadgets, and the reason we've done that rather than using a find gadget is because of the way pwntools the docs say that it hides non-trivial gadgets. So, for example, for this binary, if I list the gadgets, if I print out the gadgets, there's like 10 gadgets compared to ROPA, which finds like 97. So we could find them in ROPA and find their memory address. Instead, I've looked at the questionable gadgets function here, and then we've just used questionable gadgets plus 2 for this gadget, plus 17 for this gadget, etc. So that's basically the same anyway. We found all the same. We've just got the addresses to all the same gadgets and functions and things anyway. We also have our string here. You'll notice that we're not searching through memory to find the location of each character first, so we'll see why that is. We are setting the RAX here to our initial value as before, and you can see here that basically we say that if it's not the first loop, we want to overwrite the RAX. So it's only for the first loop that the RAX won't be modified here. And this is where we're finding the address. So rather than having a loop earlier, we're just looping now. So as we loop through each character, we find the address of that character using the same code here, and then we just print that out. And then again, we need to subtract the previous RAX value because it's incrementing each time, and we need to subtract this arbitrary value which gets written down here. And then we're just creating our ROP.raw. So for each character, we're essentially adding a dictionary of these, or a list of these gadgets. So the first gadget we're calling is our bxtr, and we're passing in the length and the index in our RDX, and we're passing in the address, which we've calculated up here, in the RCX, and the result gets put in the RBX, and then down here we call this, which will move the result from our RBX into our RAX, and then we pop our data address location into the RDI, and then finally we have this store string operation, which is going to use the .data address from our RDI and our result from all of this stuff, which is in the RAX or AL. So that's going to happen for each character, and then finally, once we've built up this nice ROP chain, we're going to call ROP.printFile. So we don't need to find the function address. We can just call printFile. We don't need to use a pop RDI because we can pass this as a parameter, and then we generate this into our chain. Create a payload where we insert the chain at the offset that we set up here at 40, and then finally write the payload to file and send it off and see if we get our flag. So let's try and run that, and you'll see it's gone through. It's found all of our memory, all of our character locations to memory, no problem. It's printed out a ROP chain, and you can see that it's also printed out the flag. And if we, because we've now saved that payload, if we now run fluff and pass in the payload, you can see here we get our flag. And that's been the fluff challenge. Hope you've enjoyed this. Any questions or any comments, any suggestions, let me know in the comments. Thanks.